Good morning, mathematicians. We're streaming live from the mountains this morning. As you can see behind me, uh, is a giant barn, which I slept in last night, uh, with actual rooms. With actual rooms. I'm probably going to keep the stream short today, so I can enjoy the beautiful outdoors that we're in. Let's go, Reddit math. But I figured I'd pop in and say hi, anyways, from the mountains. Outdoor stream, yeah. Yeah, I was too lazy to go get the plug for my, so hopefully the audio's bearable. I'm sure it's fine. But yeah, unfortunately you can't see the beautiful snow-capped mountains that are all around me. But it's nice. It's a nice place to have coffee. So let's see what's going on in Reddit. Um, let's see what's going on. Audio is good? Okay, good to know. Good to know. And good morning, by the way. Uh, wow, looks like not much has happened on Reddit since our discussion yesterday. Losing the forest for the trees. Is this graph theory? Terrible joke. Read a couple of nice books on math. These books give you a lot of love. Okay, let's take a look. Let's take a look at this. And also gave me somewhat of a sense of what's going on at research level mathematics. Always wanted to have a big objective overview of the different fields of math. But the more I learn, the more I realize how impossible that is. Yeah, yeah, it's true. Yeah, these days I can't even seem to build the frameworks for just one subject. Still do good in my classes, but feel like starting to lose the plot. Yeah, but that can happen a lot in classes. I feel like if you keep reading and learning, you can find more generalities that will help get you through. Does anyone have advice on how to get a better, more holistic view of mathematics? Um, and just subjects themselves? Well, probably reading just lots of random stuff on the internet uh, and going to talks. You had to use Euler's theorem for one of your crypto proofs. Turns out generalized Fermat's Little theorem. Plan to explore that after exam. Ah, cool. Yeah, so I guess just like a version for finite fields, I'm guessing. Multiplicative group of finite fields. That's always fun. I like that you're planning to explore it. That's good. You know, ask yourself what generality does it hold in? Feel like I lose focus, the biggest picture, because classes become harder, childish wonder seems to be disappearing. Fair, this is true. I feel like it's easy to lose this in your courses, you know? And I don't know what the antidote to it is. Uh, Maybe deliberately playing with silly things, you know? I still deliberately play with silly things. And I feel like I am, but it is easy to like, I don't know. I remember first learning about like different sizes of infinity, and this was so mind blowing. And then it's easy to become like desensitized to this as you see crazier and crazier stuff. Um, and yeah, maybe some things become demystified, but I think I don't know, maybe you have to actively try to hold on to that wonder. I mean, I'm still in love with the definition of the derivative. I still love explaining that to people for the first time, connecting the slope intercept idea, uh, y equals mx plus b, their high school understanding, and connecting that with the limit. I mean, it's such a, you know, to me nowadays, it's such a laughably basic idea, and yet somehow I'm still able to be in love with it. So I don't know, maybe it takes a lot of conscious thought. You had a nice course on topology, and you liked algebraic topology more than point set for some reason. I don't think you're alone in that feeling. I think a lot of people prefer like algebraic topology. Yeah, point set is it's almost too wild. You know, I mean, there's still things about point set topology that I like in general, but yeah, I think the thing is that mathematics, what makes a subject interesting, I think, for a lot of people, is to have the right mix of structure and chaos, right? If you have too much chaos, then everything's just hopeless, and you can't do anything, you can't say much of substance. And if you have too much structure, on the other hand, well, it's a lot of detail to hold in your head, and sometimes that makes things too rigid. You don't have a lot of examples of such things because like it's too, there's not a lot you can do. There's not a lot of moldability. And so I think the thing that algebraic topology has over point set topology is that you have, more structure. You have more structure than point set, but it's still very, very difficult and very complicated, but it's maybe a better mix of those concepts. Nice house. Looks like Grothendieck's house in the Pyrenees after IHES. Yeah, kind of. I am taking requests. I'm always taking requests for questions, yeah. But yeah, so just as I mentioned, me and a bunch of other math and stats grads have all rented a cabin out in the mountains. So that's where I'm streaming from today. Well, behind me, not even a cabin, behind me, it's actually a giant barn. And the top floor has all been converted into rooms and stuff. So that's where we slept last night. And yeah, there's like beautiful, you can't see them because they're all over on the other side of the camera, but I'm outside right now, surrounded by beautiful mountains. So it's really the ideal place to think about math. Are there complex p-adics? Very interesting question. Very interesting question. Well, technically yes, right? So first off, we have to say, well, what do we even mean? What do we even mean by complex p-adics? Well, certainly the rational numbers are a subfield of the p-adic numbers, and they're a subfield of the complex numbers, right? Now, naively, you might want to say that the rational numbers are in the intersection, but depending on how you define these fields, like set theoretically, this is kind of nonsense, right? But this already captures the idea, right? So certainly, a rational number can be interpreted either as a p-adic number, or a complex number, or what have you. There's sort of like a canonical injection into these fields, if you will. But then, okay, so what else can we say about these sorts of things? Like, are there other numbers? If you go beyond the p-adic numbers, or sorry, you go beyond the rationals. Well, it turns out, and this is actually related to the Hensel's lemma stuff I was talking about before. Out of context, but can I please find the fundamental group of RP2 using Van Kampen? I will try, but I think I've forgotten how to use it properly, because the other day I was talking to a student, and I wrote down, I was trying to do it for the torus, which is a lot easier because you don't need Van Kampen to do the torus. You just need that it preserves products. And somehow I got the wrong answer. But I will try. I will try. Because we know what the answer has to be, right? We know what the answer has to be. But that is, using Van Kampen is my least favorite way. I mean, the covering space theory is just proof is beautiful. But okay, I'll get to that in a second. So we have our p-adics. Well, the thing is, in some p-adic fields, right? Because say we want to solve like a polynomial, I want to know. So for example, just like when we go from Q, so of course the complex numbers are algebraically closed, right? So we can always solve polynomials there. What about in QP? Well, certainly if we go to R, right, we know that we've definitely increased the amount of polynomials we can solve, like x squared plus 2, or I guess x squared minus 2, right? This is now a polynomial. Can't factor it in Q, but we can factor it if we go up to R. What you mean is if we proceed, repeat the procedure, one follows when constructing the p-adics, but complex integers instead of real integers. What I mean is if we repeat the procedure, one follows when constructing the p-adics, but complex integers. I'm not sure I understand the thing about complex, but let me keep ranting, and I might hit on something in a second, because there's a lot to say on this topic. So the next thing to say, though, is, of course, now in some p-adic fields, right, in some p-adic fields, we can solve x squared plus 1. Basically, you just look at Hensel's lemma, and, well, I think I could be slightly wrong here, but it's basically should boil down to being able to solve this polynomial mod p or not, right? And so now this is just asking about like roots of 1 mod p. And so, but then of course the question is, right, the thing is, from the perspective of field theory, like, we always choose for the real numbers, for example, like we have an ordering, or like when we choose the complex numbers, we sort of take a very specific realization. But if you just build some like abstract extension that solves a polynomial, and you somehow want to like identify some subfield of this. Oh, did my pen just go? You want to identify some subfield of this with some subfield of the complex numbers, and let's say the thing is, if you can solve this polynomial, the thing is, from the perspective of field theory, you can't tell the difference between the two roots, right? So we sort of always make like a canonical choice of a square root of this polynomial. But really, there's sort of two things you can choose, so there's a possibility of different embeddings we can take. Like, for example, like Q adjoin I has two distinct embeddings into the complex numbers, where, well, let me take it to be this field, right? Either we have two distinct embeddings, either by sending x to I or by sending x to minus I. So the interesting thing is, depending on the embedding, so there isn't a canonical choice here, but depending on the choice of embedding that you make, if you can solve this polynomial in a p-adic field, then technically you could give I some p-adic expansion. So now here's another thing to say on this topic. So here's what we can do. So we have the option, we can go from the rational numbers, and we can perform a Cauchy sequence completion to get the p-adic numbers. But then another option, so that's sort of the analytic completion. The other option is to take the algebraic completion and get the algebraic closure of the rational numbers, which is Q bar. So now, the thing is, Q bar fails to be analytically complete, and QP fails to be algebraically complete, or algebraically closed. So what we can do is, well, we have two options. So one, actually, I'm not sure what happens when we take, I'm not sure what it would mean to take a completion here. I guess there is some theory of like infinite valuations. But I guess I should be careful because I don't exactly know what's going on here. But the next thing we can do is we could just algebraically complete QP to get QP bar. So now that we get, so I see stuff is going on in chat about about Van Kampen for RP2. I'm almost there. I'll tell you in a second. I'm almost there. But now, okay, so now we started with Q. We fixed the fact that Q is not analytically complete by taking this completion at a p-adic norm. But then it failed to be algebraically complete. So then we take an algebraic completion, and now this fails to be analytically complete, unfortunately. But actually, because if you have cardinality, the continuum or greater, then you're entirely determined by your, and you're algebraically closed, then you're entirely determined by your characteristic. So that means that these two fields, purely algebraically, none of the topology, these two fields are abstractly isomorphic. QP bar is isomorphic as a field to the complex numbers. And if you believe in the axiom of choice, then there's uncountably many isomorphisms, which we can never hope to explicitly describe. But this field is still analytically incomplete. But now finally, when we take the completion of that, we get something called CP. So these are the complex p-adic numbers, and this field, so definitely the topology, it is not topologically equivalent to C, very different topologies, but this is a field which, as an abstract field, is isomorphic to C, but it is also, it's a topological field complete with a different topological norm. So the analytic completion is the Cauchy sequence completion. So, given any metric space, we can form the Cauchy sequence completion, where as a set, X is all Cauchy sequences in XD. So Cauchy sequences of elements of X with respect to D, or rather its equivalence classes thereof. Yeah. Okay, so let's talk about RP2. Here's how I would go about using Van Kampen's theorem on RP2. So I would take this model of RP2, you take this gluing model. So we have, what is it? I think the arrows all go in the same direction. Is that right? Somehow it feels like what I'm writing down is the Klein bottle. Yeah. Maybe I should be doing more live streams outside, live streams on the go. Yeah, now I have to think. Am what I'm writing down? Is what I'm writing down? No, I think maybe this is RP2. But then what's the Klein bottle? I better check myself before I wreck myself, chat. RP2 is a rectangle? I don't know how to search this up. Yeah, from a square by identifying opposite edges. Okay, I was right. Yeah, okay. Everything goes in the line. Okay, nice. Yeah. So here's what we take for our open sets then. For Van Kampen, we'll take the open set U. So we carve out this little circle here. So uh, this will be U. And for other open set, uh, we'll take maybe. Wow, the sun is like rising up and shining, and it's amazing. Oh my God. Anyways, and then for V, we take this thing. We take this disk, right? And so now for Van Kampen, well, we have, let me switch. So U, in other words, is going to be, it's going to be this thing, right? And so, or sorry, let me just take this. So this is the open set that you want for U, and so we could call this like alpha, beta, alpha inverse, beta inverse, right? So you're basically going to have a loop generating the fundamental group of U. Well, okay, that's U. Let me write V is just going to be this contractible disk here. And then finally the intersection, U intersect V, is going to be this little circle. Is there a sheaf type definition that takes sets or other more primitive stuff than a topological space and converts it into some more structured object as it's traveling with the functor? Is there a sheaf type definition that takes sets or other more primitive stuff? Well, yeah. Let me pause. I'll come back to this in a second, but let me pause to say, I don't know if this is what you're after, but there is a generalization to like a sheaf. We view it as going from some sort of map from the collection of open sets into something. Let's say sets, but we could have it land in abelian groups or rings or something. But actually, really, we can view this. We can form a category out of every topological space, and the objects of this category are just given by open sets of X, and then a morphism. We have if U is a subset of V, then we say that there's a unique morphism. So that determines category. And then so viewing this as a category, this actually gives us now, instead if we take the opposite category, then a sheaf is first off a functor from this category of open sets to sets. So in other words, it's a functor from the opposite category to sets, which is the same as saying that it's a contravariant functor. But that's just a pre-sheaf. And now if you want to mimic the definition of a sheaf with like gluing and compatibility constructions, well, then you need to do a little bit more work, because you need to, somehow you need to mimic the idea of covers. And it turns out we can do that in a very categorical fashion. And that's what leads us to the idea of having a Grothendieck topology on a category. That leads us to the idea of a Grothendieck topology. And once you have that, a category together with a choice of Grothendieck topology, this is called a site. And once you have that, then you can you can mimic the gluing conditions that express a pre-sheaf as a sheaf. So that's the way to do it. Title for the stream, The Rising Sun. Yeah. Show us. Wait, Deepak, were you talking about the beautiful sun, the mountains? I don't know. I don't know if the video will pick up anything if I show you my surroundings, but yeah, I don't know if you got anything out of that, or maybe it made you barf because you spun around really quick. But yeah. Um. Okay, but hopefully, coming back to Van Kampen here, hopefully this now gives you an idea how to solve this, right? Because you're going to take a point in the intersection, and what are the loops that you're going to take to define it? Well, you should have a loop that say goes, I don't know, goes here, then it goes around the circle, and say comes back along here. So that'll be the looks very 1800s. Yeah, kind of is. There's even a wood burning hot tub here, which is pretty sweet, but it was only lukewarm yesterday. Yeah, so of course you're gonna have, right, so any loop. So if you try and look at like what the inclusion is from the factor of v, of course it'll be trivial because the v component is just contractible. U intersect v, though, you should get a loop. You should get a loop, a non-trivial loop coming from U intersect v. Are there bears? It looks like there's a place. Yeah, I'm sure there's bears around. I mean, we haven't seen any, but I brought my bear spray with me. And now, yeah, I see Daisen said something should go the other way around. So I could be wrong. Something about this might be wrong, but the idea is that if you take this loop, so the other loop, right, that'll be the thing corresponding in U over here. Somehow it should correspond to this word, right? And then I guess the thing to notice is that this term should be its own inverse. So I don't know, call this gamma. Gamma should be its own inverse, right? So hopefully this is enough for you to put the right idea for you to put the rest of this together. Is that basically, you'll basically have this one non-trivial loop, which over in U, you see will, contract to this boundary. It also corresponds as non-trivial loop in U intersect V, of course, like those loops should be equivalent. And then just recognizing that that element is its own inverse, that should basically give you enough, right? Because then if you put this all together, of course, I'm being glib and not writing base points. But if you put this all together from Van Kampen, you should conclude that this is basically just generated by this single loop. So you've got one generator, but that generator, of course, is maybe I should write the homotopy class of it. But that generator is equivalent to the identity. So this group has to be Z mod 2. And that's exactly what we expect from the covering space theory, right? Which in my mind is like the nice thing. Do I know what group cohomology is measuring? Not in general, no. I think H1 is pretty well understood. H1 in group cohomology, is there. I mean, there's various interpretations, so I don't know so much. Like, I know it's connected to like Galois cohomology and stuff. I don't know a lot about that. One day one day it would be nice to unpack the definitions and go through things a bit better. I mean, but you can also interpret. So I think if both your groups are abelian, then the H1 basically measures equivalence classes of extensions. So equivalence classes of extensions are basically, you know, E and E prime are two equivalent extensions if you have like isomorphisms of short exact sequences. So H1 will measure that. But what even is group cohomology? Obstructions to a certain kind of representations? Well, I mean, there's two, yeah, obstructions to certain kinds. I guess. I mean, well, it depends on what you mean by what is group cohomology. I mean, there's a literal definition. There's sort of two ways to do it, right? There's the sort of general way in which one takes projective resolutions and then computes the cohomology of those sequences. But then you also there's for H1, like classically, I think this thing existed, before we even had a general, like very general notion of group cohomology. So there's like, they're called like crossed homomorphisms. And so you can give like a very explicit construction of, it's like homomorphisms modulo crossed homomorphisms or something. And there's like a very explicit construction. And so for like small groups, you can use this to like explicitly construct the cohomology, the H1. Yeah. But then as for like, so there's sort of two ways to do it. But then as for what it means, I guess there's like various different interpretations. I'm not sure how to think about H1 in general. Probably it's, boils down to like extensions of a group by, I'm guessing, I don't actually know here. I'm guessing it boils down to extensions of G by the, this is the abelian group. You're taking coefficients in. Roughly, it should have something to do with this. But certainly for the higher group cohomology, I mean, I have no idea. For understanding group cohomology, is algebra 1 and linear and Li in grad enough? Maybe. Probably. I mean, I would just start reading it. I would just start. You could probably start reading about it now, and then like, as you notice things, you're like, oh, I'm a little weak on this tool that they're using. I don't quite understand it. Then you could go build that in. Yeah, semi-direct product, but for homomorphisms. Yeah, I mean the trivial class actually, if I'm not mistaken. So the semi-direct products will all be split. So somehow the trivial class, I think, should always correspond to semi-direct products. Or is that nonsense? Because I guess, no, that can't be true, because the semi-direct product won't be isomorphic to the direct product, of course. Well, it will in certain cases. So, yeah, there's something going on here with, like, semi-direct products, because those give you split sequences. But there's something weird going on. I don't recall quite what it is, but there's something weird going on, because like for modules, there's just like a direct interpretation of like X1 and split, and like the trivial class in X1 corresponding to split short exact sequences, which is, I mean, this is exactly, well, it's even more than E being isomorphic. I mean, specifically, the homomorphisms you take are important. So it's specifically when you have isomorphisms of short exact sequences in the following matter. So But then for groups, it's weirder because if I'm recalling correctly, I think it's weirder because there's something going on with like split short exact sequences of groups. And yeah, it's a little bit weirder because I think the way that split short exact sequences for groups are defined is that semi-direct products are split. And so you can definitely get like yeah, somehow you have split short exact sequences, but it's not just the trivial extension. Like it's not always just products. But my knowledge on this is fuzzy. Anyways, I've been out here yapping for long enough. Um, it's a beautiful day out here in the mountains, so I'm gonna go chill and vibe and probably do some math. But also go like hiking and hot springing and stuff. So hopefully you find a way to get up to some adventure today, but not to the detriment of proving things. Y'all better be proving things. So time to